Peterson, Berkeley, super swell guy. Thanks for coming.
Yeah, you're very welcome. So, while things are getting set up, many of you also may know this, but I'm also, over the next 2 years, going to be involved in the work of the Blue Ribbon Commission that has been formed by the administration to review U.S. policy for the management of used fuel and high-level waste. And the first thing I need to emphasize is that we're very early in this process. So nothing I say should be construed as reflecting potential recommendations of the Commission. And I'm going to focus mainly on the discussion related to work that we're doing at UC Berkeley. And anything that I do say that could be construed should be taken as being a personal opinion. And so to offer one personal opinion before starting into the presentation, you know that today we charge a nuclear waste fund fee based on the amount of electricity that a reactor generates. And of course, electricity is a good thing. So charging a fee that's proportional to the amount of electricity you make seems to be the wrong thing to do. It would make a lot more sense to charge a fee that would be proportional to the amount of waste that a reactor makes, right? And then if you think about... And the only thing I would just make an observation is that thorium is a very clean fuel. So at any rate, with that, let me dive into some discussion about work that we're doing at Berkeley. What you see here is a couple of three-dimensional views of what we call the pebble bed advanced high temperature reactor. And we've had student design groups plus a substantial amount of research work by graduate students looking at how to develop solid fueled reactors that can make use of thorium and that use fluoride salts as their coolants. And so I'll be describing that work over the next few minutes here to give some background. To start with, this is a schematic, and what you'll note here is that this looks, this is a solid fueled reactor, and so in this design we have pebble fuel, and you'll see in a moment how the pebble fuel works, with a fluoride salt. It's a FLIBE, a mixture of lithium fluoride and beryllium fluoride, as a coolant, circulating through the core, pumped by some fairly large pumps. Most of the technology that you need here actually is derived directly from the molten-salt breeder reactor. The pumps, the intermediate heat exchanger, all of those things come from the large base of engineering work that was accomplished at Oak Ridge National Lab in the 1960s and early 70s. We have passive decay heat removal, and probably the most important thing that has changed from the time of the MSBR is the fact that today we can drive closed gas Brayton cycles to perform the power conversion, and this has some substantial advantages in terms of efficiency, in terms of how compact the power conversion equipment is, and also in terms of making it much easier to mitigate against one of the only flaws behind fluoride salts, which is a relatively high freezing temperature. And using salts to heat a gas rather than to boil water is an excellent way to simplify the problem of avoiding freezing and to control for overcooling transients. Okay, so in this case, we're focused on using coated particle fuels and pebbles, and this is stretched out a bit horizontally. So at any rate, this is a type of fuel that is well developed. It turns out that in the United States, Idaho National Lab, working with Oak Ridge, has redeveloped the full capacity to fabricate, irradiate, and perform post-irradiation examination on this type of fuel. And so there's already an easy path forward in terms of developing this fuel. And because when you use a liquid coolant, you can operate reactors at much higher power density than if you use helium, it turns out that here your power density is about 6 times higher than it is in a helium-cooled modular helium reactor. It is essentially identical to the power density that you would have with Lifter. And at that power density, the seed pebbles here reach full depletion in under 1 year, which has important implications for how rapidly you can perform the fuel testing in the actual development process. So qualifying fuel for this type of reactor can be done rapidly with existing infrastructure. The coolant itself also has outstanding properties. One of the most valuable being the fact that it has a very high boiling temperature, which means that you never have to worry about two-phase flow. And having worked a lot on reactor safety for light water reactors, I can tell you that if you can eliminate two-phase flow as a phenomena, you have simplified your life enormously, right? And we also have a transparent fluid with very low chemical reactivity, and these are very positive attributes to have in terms of a coolant. But even more important is what we call volumetric heat capacity. And that is what you get. This is the product of density times specific heat. In this column here, the fourth or fifth one over. And the important thing to note is that the fluoride salts have very high volumetric heat capacity compared to any other coolants, including water. And this results in fluoride-cooled or fueled reactors being substantially more compact than any other reactors you could possibly design. And this has very important implications in terms of economics. And if you look at some of the studies that we've done at Berkeley, what you'll see is that the size of the major components in the primary loop for fluoride salt cooled or fueled reactors will be substantially smaller than even in pressurized water reactors. And of course, everything is running at atmospheric pressure, so all of the piping and other equipment can be thin-walled. And these are substantive benefits. The MSRE largely proved out major elements of the technology for using fluoride salts in its reactor coolants. And one of the things that's important to note is that while we observed corrosion and fission product intergranular attack on the primary loop of the MSRE, and work was done to resolve that in terms of improving Hastelloy-N, but the work to fully qualify Hastelloy-N was not fully completed. When you work with a clean salt, which you can do when you use a solid fuel, the clean salt was used, and the intermediate loop was identical, except there was no fuel dissolved in it. And the intermediate loop on the MSRE operated for over 24,000 hours without any detectable corrosion whatsoever. And so this is one of the reasons why at Berkeley we've been focused initially on the solid fuels, is because we think that you've taken a few of the major issues off of the table that make it easier to move forward to demonstration and commercialization. And this leaves you with a smaller set of steps to take to move to the liquid fuels, which enable you to remove fission products and make thorium work at conversion ratios of 1 or greater. These reactors with solid fuel, it would be a challenge and probably not possible to economically run them at conversion ratio of 1. So they will be converter reactors. Okay. In terms of economics, we can make some high-level observations that suggest that these class of reactors will have lower energy costs than light water reactors. As I mentioned, the entire primary loop ends up being more compact, except for the reactor vessel itself, which is not enormously different from a light water reactor. You have no sources of stored energy to pressurize a containment. So in fact, you can have a low leakage, compact containment. And then with gas Brayton power conversion, of course, you have substantially higher power conversion efficiency. Compared to fast reactors, basically studies that have been done indicate that the cost of electricity coming from reactors based on fluoride salt technology will be somewhere in the order of 1/2 the cost of electricity coming from sodium fast reactors. And this comes about largely from the fact that sodium has a very low volumetric heat capacity, and so the equipment ends up being very large and bulky. Reactor vessel on something like an S-prism will have 5 times the volume per unit of electricity generation of a fluoride salt cooled reactor. And so this is an important difference. Also, you have, in the case of the fluoride salts, no need to design a containment to sustain substantial pressure as you do with sodium. And the final point is that fast reactors, because of the fast neutron fluence, require the use of metal fuels. There's work to develop ceramic fuels, but it's very challenging for fast spectrum to do that. And In the case of metal fuels, you have very clear limits on the maximum outlet temperature. Thermal spectrum reactors cooled by fluoride salts can be designed for any temperatures up to probably 1,000 degrees centigrade. With currently available materials, we can operate with an outlet temperature of 700 degrees centigrade, which puts us firmly in the space of temperatures where you can drive a gas cycle. And making the transition to a gas cycle is probably one of the single most important evolutionary steps to take with nuclear energy, because boiling water is an ancient technology and the fossil people have already gotten well away from boiling water. And the cheapest, lowest capital cost technology is definitely a closed gas cycle. And then finally, modular helium reactors, you can just see the size comparison there. Going to a liquid coolant brings substantial advantages relative to what you have with high pressure helium cooled reactors. Okay, there's also interesting characteristics from the perspective of safety. In AHTRs, one has over 500 degrees of temperature margin between maximum temperatures that can be achieved under any credible scenarios in terms of accidents and transients, and fuel damage temperatures. And this is also completely different from any other class of reactors. Now, in the case of Lifter, it's important to note that you have the same basic benefit. That is, your core structures can accommodate vastly higher temperatures than you could ever reach in any sort of transient. So you never worry about accidents that involve core damage due to thermal problems, as opposed to all of the reactors that make use of metallic core structures where peak temperature in those structures is usually a major constraint on the coolant temperature. You also have the benefits of having essentially no stored energy sources, so you can have low leakage, low pressure containment, and this also by placing all of the primary loop equipment in that containment without insulation and insulating that volume, you can control against overcooling transients. You can add around that a filtered confinement. And then finally, you have an additional barrier that's provided by the external event shield. And therefore, you actually have, in addition to very large margins of thermal damage, at least 1 to 2 more barriers than any other reactor concepts. And pretty much the same thing applies to Lifter, except instead of using the very robust high temperature fuel, what you're doing is continuously removing the mobile fission products so they're not a part of any accident scenario. Right? Okay. We've been doing work on a number of different scaled experiments that take advantage of the fact that with water, you can match Reynolds and Froude number and the hydrodynamics essentially exactly. So we can look at hydrodynamic phenomena such as pebble recirculation very nicely in scaled experiments. And then we've also been working with oil, which can match Prandtl number and do heat transfer. What you see here is a demonstration that we can generate radially zoned pebble cores, which allow us to implement thorium blankets. And you'll hear more about the implications from that when Tommy Cisneros talks later today. This goes to the point that was made about fissile startup requirements. If you take a quick look, AHTRs are in the same class as MSRs, is essentially requiring almost no fissile to start up. So there is no constraint based on fissile availability in terms of expanding. There's enough fissile in the world to start up as many AHTRs or MSRs as you might want. It is not a constraint on the dynamics. And if you wanted to shut things down, it's a lot easier here too. So that's an important point. And then just some quick comparison. Basically, the big difference with fast spectrum reactors is the much lower fissile startup requirements, but also this other set of things that are associated with the capability to go to much higher burnups because you're not using metallic fuels and having a much more compact system. Light water reactors, well, you can reduce your uranium consumption substantially compared to conventional reactors. You can also work using recycled transuranics from light water reactor spent fuel when you have these large thermal margins. And then the other thing is to compare with Lifter itself. And the key thing here is that you are working at lower conversion ratios. So this is not a long-term sustainable technology, but it is a bridge because it will be, and I can promise you it's simpler to these days license a solid fueled reactor than a liquid fueled reactor. Okay, just some quick comparisons because I want to leave a little bit of time. In general, what we find is that the building volume of a fluoride-cooled reactor that is small and modular still ends up being on the order of half the building volume per megawatt electric of light water reactors. Almost certainly, the economics are substantively better here than current light water reactor technology. You can also make comparisons of the primary loop component sizes between AHTRs, lifters, and sodium fast reactors. And you'll note that essentially here, everything is substantially more compact. In fact, the reactor vessel volume scales almost perfectly with the volumetric heat capacity of the two coolants. So some conclusions. Well, the AHTR development path is attractive because we're making use of currently available materials. Getting code certification on any new materials is a 15 to 20 year process. So as soon as you propose a reactor that needs new materials, you've basically said something that's going to be deployed in 2030 to 2040, okay? We also can use existing fuel irradiation capacity that's already here in the United States. As soon as you propose developing a new fast spectrum fuel, you're probably 20 to 30 to 40 years in the future because the irradiation capacity for fast spectrum stuff is just almost non-existent in the world. The licensing approach actually can be adapted quite nicely from what we do with advanced light water reactors. And then you have this potential actually to achieve much better economics than we get from current reactor technologies. And it's, I think, a better idea to look toward technologies that have the potential for improved economics. And with that, I'll go ahead and stop and take any questions.
Rock that.
Yes.
I'm Charlie Bowman from Adna Corporation.
Hi, Charlie. It's been a while.
Yeah, a very nice talk. I wanted to ask the question about power density. You arguing that that's an advantage for this system. Mm-hmm. We're working with systems that are lower power density, and we see that as an advantage because of the afterheat removal problem, which mm-hmm. becomes more of a problem the higher the power density is, and by working with the lower power density graphite molten-salt reactor that we've designed, this is a problem that's easily dealt with by natural convection. How do you deal with your with that problem?
And we have detailed relap models, and we're in the process under DOE funding of building an integral effects test facility that will replicate the natural circulation phenomena that remove the heat. There's no problem that the removing heat at this power density by natural circulation is not the constraint on the design. Most likely, the thing that limits temperature is the need to keep the temperature of the primary loop structures below the code limits. And the thing that's limiting power density right now looks like it's going to be a dose to the center reflector of this design. And we think that will be in the range of 20 to 30 megawatts per cubic meter. Certainly there's no thermal limits on the fuel. We have hundreds of degrees of margin to fuel damage, so that's not even close to being an issue.
Oh, I got a question.
Okay.
You know, I always hear about these incredibly long lead times, and, you know, working in private industry, you know, mm-hmm. I just can't fathom is it for sure 15, 20 years of lead time, or is that just what we've come to over the years with the NRC regulations? Is there a way where we'll get into an existential enough situation where we decide, hey, you know what, 4 years, that's pretty good right there?
If you want to develop an ASME code case for a new material, it's 15 years. I don't think that we've done anything in the last 40 years to compress that down. We need to remember that there's two types of phenomena that are important in the licensing of reactors. There's the things that relate to safety, which means response under transients. Transients are short, and so we can actually do empirical work and experiments to understand safety-related things in a compressed period of time. The other things we worry about relate to the reliability, and that relates to the corrosion of materials, things that degrade fuels, and materials-related phenomena such as response to neutron irradiation. To understand those things empirically requires long periods of time, inherently, And so as soon as you propose reactors that need new fuels or new materials, you need to recognize that it's going to take a while to qualify those new technologies intrinsically because you're interested in phenomena that evolve over long periods of time. And trying to compress that is tough to do, although you can do it, to get to a bit, you can do that. But in the end, for example, when you propose technologies like long-lived cores, qualifying the materials and fuels for a long-lived core is tough. And the Navy has gotten there, but that's with, 60 years of work. So if you want to do new materials or new fuels, you need to recognize that you're talking about multiple decades to commercialize.